This is AP Calculus AB. We're looking at notes 1.8, infinite limits and limits at infinity. Should note that once we learn L'Hopital's rule, and we can't learn it yet because there's too many rules that are needed in order to use L'Hopital's rule that we haven't learned yet, this entire section becomes much, much, much simpler. Infinite limits. An infinite limit is a limit that results in positive or negative infinity when x is approaching a number a. Justification for the existence of vertical asymptotes using limits. X equals a is a vertical asymptote for f of x if and only if the limit of f of x as x approaches a from the left goes to positive or negative infinity, and the limit of f of x as x approaches a from the right equals positive or negative infinity. Let's look at this picture here. Now we can clearly see from this picture there's a vertical asymptote here at 2. If we were to use our pre-calculus skills and set our denominator equal to 0, x squared minus 4 factors into an x plus 2 and an x minus 2. X plus 2 is a canceling factor. There's going to be a hole at x equals negative 2. X minus 2 is a non-canceling factor of the denominator. Therefore, we have this vertical asymptote at x equals 2. What we are trying to do is use the calculus justification for the existence of a vertical asymptote using limits. So what we would say is, that this graph has a vertical asymptote at x equals 2 because as x approaches 2 from the left, the limit is approaching negative infinity. Or we could say, as x approaches 2 from the right, the limit of f of x is approaching positive infinity. If you approach a number from the left or the right, and f of x is approaching positive or negative infinity, then that means there's a vertical asymptote. Question 1. What's the limit of f of x as x approaches 2 from the left? As we approach 2 from the left, it's approaching negative infinity because it's going down forever. What happens if you approach 2 from the right? Well, this function is going up forever. It's approaching positive infinity. What's the limit of g of x? Whoa, g of x. G is over here, f was over here. So now we're looking at this graph. What's the limit of g of x as x approaches negative 1 from the left? Well, here's negative 1. If we approach from the left, it's going to negative infinity. What's the limit of g of x as x approaches negative 1 from the right? If you approach negative 1 from the right, it's going up forever. It's going to infinity. Just going to make a note here that both of these problems are using the graph over to the right. Find the limit indicated. Explain what the results of the limit means about the graph of the given rational function. Now we just did this problem. It was the one above in the picture, but now we're going to do it algebraically and see what happens. If we try to evaluate the limit directly by putting 2 in here, you're going to end up with dividing by 0, which is undefined. So if we factor the numerator and denominator, the numerator factors into a 2x plus 3 and an x plus 2. To find that, you'd split the middle term and factor by grouping. The denominator factors into an x plus 2 and an x minus 2, because the denominator is the difference of 2 squares. We have a canceling factor on the top and the bottom. That means there's a hole at x equals negative 2. We have a non-canceling factor in the denominator of an x minus 2. That means we have a vertical asymptote at x equals 2. But we are supposed to use calculus to figure this out. We can clearly see that we still can't use substitution for this. It's going to be undefined. We're going to be dividing by 0. So we know there's a vertical asymptote. What we don't know, without looking at the graph, if we approach 2 from the left, is this going to approach infinity or is it going to approach negative infinity? To figure that out, we're going to use a little table off to the side. We're going to choose an x value to the left of 2, something super close, like a 1.9. We're going to plug that into what's remaining of this function. Our only concern is this number going to be positive or negative? Well, if I put a 1.9 into the top, 2 times 1.9 plus 3, that's going to be positive. If I put a 1.9 into the bottom, 1.9 minus 2, that's going to be a small number and it's going to be negative. If you divide a positive and negative, you get a negative. That tells us that this limit is going to be approaching negative infinity. It's going down forever. Number 3, essentially the same work, it's the same function, but now we're approaching from the right of 2. So we want to know if we're approaching from the right, if we're approaching the vertical asymptote from the right, does this mean that the graph is going up or down forever? So once again, if we make a little table with x and y, pick a number to the right of 2, something super close, like a 2.1. If you put that into the numerator, 2 times 2.1 plus 3 is positive. Denominator 2.1 minus 2 is negative. No, it's positive. If you divide two positives, you get a positive. That tells us that if we approach this vertical asymptote from the right, it's going to be approaching infinity. Let's go back to the directions. Find the limit indicated. We did that. Explain what the result of this limit means about the graph of the given rational function. According to the limit existence theorem, this means that the function f of x has a vertical asymptote at x equals 2. And the same can be said down here. Since we're approaching 2 from the right, and that limit is going to infinity, then f of x has a vertical asymptote at x equals 2. The reason we're saying it's f of x is because this is all referring to this function right here. And if you look at your graph, you can clearly see this confirms what we said when we did the algebra. An infinite limit always yields a vertical asymptote. Limits at infinity, as opposed to infinite limits. A limit at infinity is a limit in which x is approaching infinity or x is approaching negative infinity. As opposed to infinite limits, we're saying y is approaching infinity or negative infinity. Justification of the existence of a horizontal asymptote using limits. Y equals c is a horizontal asymptote of f of x if and only if the limit as x goes left forever, negative infinity, the function is approaching a number, or as x approaches infinity, it's going to the right forever, y is approaching a number. Looking at this picture, actually, the first question here, f and f, is referring to this picture over here. As x approaches infinity, as it goes to the right forever, what's happening to y? Well, it's getting closer and closer to this horizontal asymptote of 2. As x approaches negative infinity, as it goes to the left forever, it's getting closer and closer to this horizontal asymptote of 2. Using this picture, as x approaches infinity, it looks like this y value just keeps going up and up and up. So it is approaching positive infinity. As x approaches negative infinity, this y value keeps going down. It's approaching negative infinity. Notice the difference between those two answers, 2 being function f and function g. Function f, according to the existence of a horizontal asymptote using limits, this must have a horizontal asymptote at y equals 2. This one here at g, as we go left and right forever, does not approach a number, so it doesn't have a horizontal asymptote. All right, number 5. Find each of the following limits at infinity. Explain how you arrived at your answer. Well, we're going to look at this big picture standpoint. This goes back to pre-calculus and our knowledge of parent graphs. In order to describe the end behavior, And keep in mind, if it says x is approaching infinity, it's talking about end behavior. We have to know if this function is going up or down as you're going left or right. And to determine that, we have to know two things. We have to know, is the function even or odd degree? And we have to know, is the function's leading term positive or negative? By knowing those two things alone, we can figure this out. So looking at number 5, this leading term is negative for sure, and the leading exponent is odd. So all you got to think about, do I know an odd function? I sure do. A line is an odd function, y equals x. And if the lead term is negative, that means it's going to be going like this. So as we go right, it goes down. As we go left, it goes up. This is asking what happens to x, or what happens to y as x goes to the right. Well, it's clearly going down. So this limit is negative infinity. And I know all that because of the end behavior that we learned from pre-calculus. I'll explain how you arrived at your answer. Well, the function is odd degree with lead coefficient negative. Therefore, the graph falls to the right. So as you go right, it goes down is what that means. Let's look at this next one, number 6. First of all, what's the degree of this? Well, if we if we take 4 minus x times itself because it's squared, this is going to end up with a positive x squared. If we then multiply that by this x and this x, we're going to get a positive x to the 4th. So this is going to end up being a positive x to the 4th and then a bunch of other terms that we don't necessarily care about. This is an even degree, and it's a positive lead coefficient. So what kind of graph has the same end behavior as that? Well, simply a parabola that opens up. So we could say, well, first of all, what's the answer to this limit? The answer is positive infinity. As we go left, it's going to go up forever. So we could say the function is even degree Make sure you don't just say it's even. If you say the function's even, that means it's symmetric to the y-axis. And that is not what we're saying. We're saying that the degree of the function is even. And the lead coefficient is positive. Therefore, the graph rises to the left. As you go left, it goes up, is what that means. Number 7. Now, this is a little more complicated. For this function, we don't know what this parent graph looks like. It's not one of the things that we've memorized. But remember, as x goes to the right, we're describing the end behavior. A rational function has the potential of the end behavior approaching a horizontal asymptote, or it could approach a slant asymptote. Something we discussed in pre-calculus. How do you figure out where the horizontal asymptotes are? Well, if the degree of the numerator and denominator are the same, we're going to change that wording a little bit in calculus, but they are the same because they're both to the first. We could rewrite this as negative 2x plus 3 if you prefer. Then this has a horizontal asymptote at y equals, you take the leading coefficient in the numerator and divide it by the one in the denominator. That would be negative 2 over 1. So that means that as this goes to the right forever, it's approaching the horizontal line of negative 2. So instead of saying that the degrees are the same and all that for this horizontal asymptote, here's how we're going to change our wording. We're going to say the numerator and denominator grow at the same rate. Therefore, there's a horizontal asymptote at y equals a over b. A in this case is negative 2 and b is 1. Those are the lead coefficients in the top and the bottom. Therefore, the graph approaches negative 2 as x approaches infinity. Graphically, a limit at infinity can yield a horizontal or slant asymptote. Well, that's not entirely true. Or it can produce neither. It can go to negative infinity or positive infinity. All right, third example. The third example that we just did provide a basis for developing our analytical process, which we find the limits at infinity for all types of rational functions. Before we can do that, let's investigate the two functions below graphically and numerically. Graphically, we can clearly see that as this function goes to the right forever, it's getting closer to the horizontal line of y equals 0. As you go left, the same. Second function, as you go left or right forever, it's also approaching the horizontal asymptote of y equals 0. What do each of these functions have in common? Algebraically, well, let me tell you. Algebraically, the numerator or the denominator grows faster than the numerator. So looking at this is 3, it's a constant, it's not growing at all. X is going to grow faster whether you go left or right, faster than 3. Either it's going up or down, it's growing at a faster rate because it has a slope of 1, whereas this has a slope of 0. X squared grows faster than 1. 1 has no growth whatsoever. X squared clearly grows faster than x. What do they have in common graphically? Both graphs have a horizontal asymptote at y equals 0. Let's sum this up here. When it comes to finding limits as x is approaching infinity, trying to find horizontal asymptotes and slants and things, there's a horizontal asymptote at y equals 0 if numerator and denominator, that's not true. Sorry. If denominator grows faster than the numerator. There is a slant asymptote at y equals a over b if denominator and numerator grow at the same rate. That growth rate is determined by the type of function it is. It is not determined by coefficients. And then there is no, you know what, I'm sorry, I wrote slant asymptote. This is a horizontal asymptote at y equals a. There is no horizontal asymptote if numerator grows faster than denominator. As far as slant goes, you can write this down if you want. For slants, if the numerator, if its degree is exactly one more than the denominator, is going to be a slant asymptote. All right, number 8. For each function below, divide every term in both the numerator and denominator by the highest power of x that appears in the denominator. Then evaluate the indicated limit. Does the result of each limit make sense based upon the graph that is pictured? You won't have to do this once we learn L'Hopital's rule. L'Hopital's rule makes this question 8, with all these problems underneath of it, super, super simple. So before we get into this, let me belabor a point. I'm just going to write this down up here. The limit as x approaches infinity or negative infinity of 1 over x is 0. Now the reason it's 0, looking at graphs, if this bottom is growing faster than the top, we just established there's a horizontal asymptote at 0. So as the graph goes right forever, it's getting closer and closer to that horizontal asymptote. Using a table of values, let me try to illustrate this. Say we have x and we have 1 over x. I'm going to approach infinity. So let's say we have 1, and then 10, and then 100, and then 1,000, etc. Well, if I put a 1 into this, 1 divided by 1 is 1. If I put a 10 in it, it's going to be 1/10. If I put 100, it's going to be 1/100th. If I put 1,000, it's going to be 1,000th. Hopefully you can clearly see as x gets bigger, these y values are getting closer and closer to 0. If I were to put 1,000,000 into the top, I would get 1,000,000th in the bottom. Doesn't matter if it's positive or negative. If this was x is approaching negative infinity, these would be negative numbers. These would just be the same here, but they'd be negatives. The point is, if you have 1 over x, and this 1 could take many forms, it could be any constant, the limit as x approaches infinity or negative infinity is going to be 0. That's a concept we're going to use to try to do these problems. So let me try to explain. As it says here, we are going to divide every term by the highest power of x that appears in the denominator. So looking at this first one, the biggest term in the denominator is x squared. So we are going to we're going to multiply this by 1 in the form of x squared over x squared. I need to restate that. We're going to multiply this by 1 in the form of 1 over x squared over 1 over x squared, which essentially means we're going to take all the original terms and we're going to divide them by x squared. That's what that means. I'm just going to use different colors for your viewing pleasure. Then we simplify this. X divided by x squared is going to be 1 over x. 2 over x squared doesn't simplify. In our denominator, we're going to have 1 plus 5 over x plus 6 over x squared. They may not realize it yet, but that just makes this problem Super easy. Remember, when you evaluate a limit, you can evaluate each term separately. If you have a fraction, you can evaluate the top and bottom separately. So what's the limit of this function as x approaches infinity? Well, what's 1 over x approaches infinity? We just said that's going to approach 0. What's 2 over x squared approach as x approaches infinity? Well, as this number gets bigger on the bottom and bottom, as the number on the bottom gets bigger and bigger and bigger, this fraction is going to be closer and closer to 0. On the bottom, 1 is going to approach 1, 5 over x approaches 0, and 6 over x squared approaches 0. We end up with 0 over 1, which is 0. So this limit approaches 0. Now the picture clearly shows that, but we wouldn't have a picture. As x approaches positive infinity, the graph is approaching the horizontal asymptote of 0. Let's try this again. Now we're going to negative infinity. It's the same function. We're going to divide each term by x squared, because that's the largest degree in the denominator. We simplify each of these. When you divide something by itself, it cancels. X over x squared is 1 over x. 2 over x squared doesn't simplify. X squared over x squared is 1. 5x over x squared is 5 over x. And 6 over x squared doesn't simplify. Evaluating the limit, 1 over x approaches 0 as x approaches negative infinity. 2 over x squared also approaches 0. 1 approaches 1. 5 over x approaches 0. 6 over x squared approaches 0. This is 0 over 1, which is 0. Graphically, as we go left forever, it's getting closer to the horizontal asymptote of 0. Let's try another. This got a little jacked up. This is supposed to be over here. I don't know what happened. So once again, you wouldn't have this picture. So the picture is just there just to confirm our results right now. As we approach infinity, we are going to divide every term in the top and the bottom by x squared, because that's the largest degree in the denominator. That's equivalent to multiplying by 1. So we're going to have 2x squared over x squared plus 7x over x squared plus 6 over x squared. In the denominator, we get x squared over x squared plus 5x over x squared plus 6 over x squared. Until you evaluate the limit, you got to keep using limit notation. This becomes 2 because the x squareds cancel. This becomes 7 over x, and 6 over x squared doesn't change. Denominator, we get 1 plus 5 over x plus 6 over x squared. 2 is going to approach 2 as x approaches infinity. This is going to approach 0. This is going to approach 0. This is going to approach 1, 0, and 0. That's going to give us 2 plus 0 plus 0 over 1 plus 0 plus 0, which is 2 over 1, which is 2. If we go back to precalculus, we knew this all along. This is asking to find horizontal asymptotes because it's asking for the end behavior because x is approaching infinity. Top and the bottom grow at the same rate. So we have a horizontal asymptote at 2 divided by 1, which is exactly what we got here. See if we can shorten our work a little bit for this. We are going to divide every term in the numerator and denominator by x squared. So 2x squared divided by x squared is 2. 7x squared divided by x. 7x divided by x squared, 7 over x. 6 divided by x squared is 6 over x squared. The denominator, x squared divided by x squared is 1. 5x divided by x squared is 5 over x, and 6 divided by x squared is 6 over x squared. To evaluate the limit, 2 is going to approach 2, 7 over x approaches 0, 6 over x squared approaches 0. As x approaches negative infinity, 1 is going to approach 1, 5 over x is going to approach 0, 6 over x squared is going to approach 0. So this is also 2. Now the graph confirms this. As you go left to right, you're approaching y equals 2. There's a horizontal asymptote there. This next one, in this case, we would divide every term in the top and bottom by x. Show all the work for this going to infinity, and then we'll skip a little bit of work when we go to negative infinity. So we're going to divide x squared by x, 3x by x, and 2 by x. Going to divide x by x and 1 by x. X squared divided by x is x, 3x divided by x is 3, 2 over x is 2 over x. X over x is 1, and 1 over x can't be changed. Now what is x going to approach as x approaches infinity? Well, it's clearly going to approach infinity. Then we got plus 3, 2 over x is going to approach 0. In our denominator, we got 1 minus 0. Infinity plus 3 is still infinity. You divide that by 1, you're going to get infinity. So this limit does not exist. For a limit to exist, it has to approach a number. If you want to know what the end behavior is like for this, as x goes to the right, this is saying y is going up forever, which is what this is saying. So from the left, let's divide each term by x, because that's the biggest degree in the denominator. X squared divided by x is x. 3x divided by x is 3. 2 divided by x is 2 over x. X over x is 1, and then 1 divided by x is 1 over x. To evaluate this limit, we're going to put negative infinity in here. So x is going to approach negative infinity. 3 is going to approach 3. 2 over x approaches 0. 1 approaches 1, and 1 over x approaches 0. This is all going to result in negative infinity, which means the limit does not exist. Confirmation, as we go left forever, the graph's going down forever. Suppose the following limits were given to you in multiple choice. What would the result of the limit be? Base your reasoning on intuitive understanding of the graph of the function. So if this was multiple choice, I would simply look and I would say, if this is saying x is approaching negative infinity, it's asking for horizontal asymptotes, end behavior. The top and the bottom are growing at the same rate because they're both x squared. Therefore, the horizontal asymptote is the lead coefficient on the top divided by the lead coefficient on the bottom. This graph has a horizontal asymptote at y equals negative 2/3. That's all you got to do. Here, let's see, the top's growing faster than the bottom. That means there's no horizontal asymptote. It does mean there's a slant asymptote. To find the slant asymptote, if we were to use long division, you would find that it's negative 2x. Now you could also use synthetic division. That would work as well. Let's just go through that real quick. So if we take 2x, 2 minus 2 and a negative 1 and a 5, and if, well, that gets complicated. Let's do this. So we know that there's no horizontal asymptote. We do know there's a slant, but that really doesn't matter because knowing that there's a slant, not necessarily all that helpful. What we want to know is this going to go up or down forever? Because there's no horizontal asymptote, it's going to be going up or down forever. So to determine that, we're going to let's pick a negative number that's big and decide what's going to happen here. So for example, if I put a negative number into x squared, the squaring is going to make it positive. If I'm subtracting a negative number, that's going to make this positive as well. So this whole top is going to be positive as x approaches negative infinity. As far as the bottom goes, 3 minus x, if x is negative, because it's going to negative infinity, it's going to be 3 plus x. I'm dividing a positive by a positive. That means this is going to positive infinity. Getting close. The algebraic analysis described above to evaluate a limit at infinity can be used to find limits at infinity. Once again, these problems that we're doing right now, if they seem super hard, they will not be hard once we learn how to use L'Hopital's rule. It will not be hard at all. And I can't wait till we learn that. It's not going to happen for a long time. Okay, what is one thing that you notice is different about the graph of this rational function versus what we learned in the past? Well, this has two horizontal asymptotes. And I don't think we've ever encountered that before. Just looking at this picture, as x goes to the left forever, this graph's getting closer to the horizontal line y equals -2. As x goes to the right forever, it's getting closer to the horizontal line of +2. There's two horizontal asymptotes. Now the question is, this is number 10 and 11 on the next page, the same problems without a graph. The question is, how would we know what this is approaching without a graph? Let's see if we can figure that out. We're going to use the same strategy that we used before when we're going to infinity or negative infinity. We're going to divide by the biggest degree that's in the denominator. We're going to divide every term by that. Now, the denominator, what's confusing about this is this radical. So at first glance, you might think, well, x squared is the biggest degree in the denominator. Well, it really isn't, because we're going to square root that. The square root of x squared, well, that's x. But it's still not that simple. So let me write this down and we'll try to reason this out. If x is less than 0, and it clearly is because it's approaching negative infinity, then if you take the square root of x squared, what should you get for your answer? Should you get a positive number or a negative number? Well, you should get a negative number because it clearly says x is less than 0. So this is going to give us a negative value. So we are going to take this limit as x approaches negative infinity, and we're going to divide each term by a negative x. Now when I put this inside this radical, it makes it an x squared. That's the part that's confusing for lots of folks. Because if I square root an x squared, I should just be getting, the x or the negative x. Now as far as these limits go, this could be simplified, and I can make this the limit as x approaches negative infinity of -3 plus 2 over x. In a denominator, I'm going to get 2 plus 1 over x squared. To evaluate this limit, As x approaches negative infinity, negative 3 is going to approach negative 3. 2 over x is going to approach 0. Square root of 2 is going to approach square root of 2. 1 over x squared is going to approach 0. This ends up being negative 3 over the square root of 2. Now this is not very different from what we learned in pre-calculus. That process was ridiculous and different. But let's go back to the beginning. Are these growing at the same rate? They are. This is 3x, focusing on the x. This is x squared, square root of that, which is x. They're growing at the same rate. So we should be dividing by the lead coefficients, which is 3 and the square root of 2. The difference is, since we're going left forever, we'd be using a negative number for this, which is going to make this negative. Another way to look at it. If I put negative infinity into this, into the top's going to be negative. 3 times negative infinity is negative, minus 2 is negative. If I put negative infinity into the bottom, a negative squared is positive. 2 times a positive is positive. Positive plus 1 is positive. Square root of positive is a positive. So you get a negative over a positive, which is going to make it a negative. This process right here will disappear once we learn L'Hopital's rule. Number 11. Oh, this is a different problem, isn't it? I thought we were doing... These are different functions than they were on the front. I thought they were the same ones. My apologies. So in a similar fashion, if x is less than 0, then the square root of x squared is going to be a negative number. So we're going to divide by a negative x, each of these terms. That's going to look different depending if it's inside a radical. So x squared over negative x plus 2x over negative x. In our denominator, we're going to have 3x squared. Since this is inside a radical, we have to square it to put it inside. The negative x squared is a positive x squared. Now this simplifies a bit. We're going to get negative x minus 2 over x. And we got the square root of 3 plus 2 over x squared. To evaluate the limit, we're going to put negative infinity in for this. We're going to have a negative infinity minus 0. I'm sorry, I made a mistake here. This was 2x over negative x. It's going to make this simplify to negative 2. Apologies. In the denominator, we're going to have the square root of 3 plus 0. A negative infinity is positive. Positive infinity minus 2 is positive infinity. If you divide that by square root of 3, you're going to get positive infinity. So this limit does not exist. But we do want to know that it's approaching infinity. How could we have done this with pre-calculus? What's growing faster, the top or the bottom? The top is x squared. The bottom's growing by x, because the square root of x squared is x. X squared over x, the top's growing faster. So that means that we know this can't exist. There's no horizontal asymptote. All right, that concludes these notes. Do not freak out majorly if you leave this section thinking, holy cow, I can't handle this. We will at one point learn L'Hopital's rule when we're ready, and it's going to make this much